In this video, you'll be introduced to a simple model of bonding that can be employed to transition metal complexes, crystal field theory. We will go through the basis of the theory in a mathematically non-rigorous manner, and then understand why the d orbitals in OH and TD complexes have the different energies that they do. Since their discovery, it has been known that molecules containing transition metal ions had different properties than molecules derived from main group elements. These compounds displayed a wide variety of different colors, magnetic behaviors, and reactivity patterns that differ dramatically from their main group counterparts. Beginning in the late 1920s, scientists started to employ quantum mechanical treatments to understand the electronic structure of simple molecules such as dihydrogen and dioxygen. From these studies, one could start to understand different facets of their properties, such as why dioxygen possesses a paramagnetic ground state. Given the success of these early quantum mechanical treatments, scientists started to think about how they could employ such methods towards understanding the properties of transition metal complexes. Two scientists that had much early success in this regard were Hans Bethe, who was working in Germany at the time prior to his escape to the United States, and John van Vleck from the United States. The two of these scientists are credited with the formulation and development of what we now call crystal field theory. At the time crystal field theory was developed, even the large approximations that were made to simplify the mathematics of quantum theory applied to molecules were computationally daunting when applied to transition metal complexes. Therefore, a number of approximations were made in the development of crystal field theory so that it could be used as a useful physical model. The biggest approximation that was employed involved the nature of the bonding between the metals and the ligands. To understand this approximation, we're first going to consider the molecule titanium hexachloride. Titanium hexachloride contains a formal titanium 3+ ion which contains one d valence electron. The titanium center in this molecule is surrounded by 6 chloride ions in an octahedral geometry. This is therefore similar to the sodium ion in the sodium chloride structure, which contains a sodium ion surrounded by 6 different chloride ions. The bonding in sodium chloride was known at the time to be largely ionic in nature. Therefore, the assumption was made that to a first approximation we can consider the bonding between the transition metal ion and its ligands as being ionic in nature. When this is done, we can consider the titanium ion surrounded by 6 negative charges, and that electron, that valence electron, will interact with those 6 negative charges surrounding the titanium center. Quantum mechanically, we describe electrons using wave functions, so that d electron can be described by using one of the 5 3d orbitals, the 3d x squared minus y squared, dx squared, or I should say dz squared, dxy, dxz, and dyz. What we're now going to do is consider how these d orbitals behave in 3 different situations. The first situation that we're going to look at is if these d orbitals are in a vacuum, so they're not being exposed to any external field. In a vacuum, all of these d orbitals will have the same energy. They'll be 5-fold degenerate. So there's going to be no influence on the relative energy of one orbital relative to the other orbital when it's contained in a vacuum. We're now going to embed these orbitals in a spherical field of a 6 negative charge. This spherical field will look something like this. Once again, spherical field, it's completely symmetric. Because it's completely symmetric, all of those d orbitals will be destabilized. They're destabilized because we have negative charges interacting with that electron. That's a destabilizing influence. But because it's spherical, all of those d orbitals will be destabilized to the same degree, meaning that they'll be 5-fold degenerate in energy. We're now going to take this spherical field and we're going to localize those charges in an octahedral field. So when we apply this OH field, we now have some directionality associated with that field, meaning that it's going to interact with some of those orbitals more strongly than other orbitals. Looking at these, you might notice that the dz squared and the dx squared minus y squared have those orbitals oriented directly on the molecular axes. So they're pointed directly towards those negative point charges. Those are going to be more strongly destabilized than those orbitals where those lobes are off axes. So the dxz, the dyz, and the dxy all have those lobes oriented off axes, so they're going to be less interacting and therefore less destabilized by those negative point charges. So dz squared, dx squared minus y squared, more destabilized, dxy, dxz, dyz, less destabilized. We can see how this progresses on an energy level diagram. So on this energy level diagram, we start off with the 3d orbitals in a vacuum having 5-fold degeneracy. You apply that spherical field, they all get destabilized by the same amount. They're still 5-fold degenerate because it's a spherical field. We're now going to apply that OH field, so we have directionality now in the field, which means that some orbitals are going to be more destabilized than other orbitals, and we get this splitting in an OH field. The dz squared and the dx squared minus y squared go up in energy relative to the spherical field, while the dxz, the dyz, and the dxy go down in energy relative to that spherical field. The amount of energy that these orbitals are split by in an OH field is termed 10dq, or delta O. D and Q are energy parameters that have been derived elsewhere. For our purposes, all you have to know is that the energy that is split by is 10dq. I should point out in general that the difference in energy between different orbitals within the crystal field model is termed delta. Here we give this delta O to signify it's the splitting due to an octahedral field. In the crystal field model, the energy at which the orbitals are stabilized and destabilized is conserved relative to the spherical field. So if we generate a barycenter, what we find is that the dz squared and the dx squared minus y squared are destabilized by 6dq, or 3/5 delta O, while the dxz, the dyz, and the dxy are stabilized by 4dq, or minus 2/5 delta O. This stabilization and destabilization is done to conserve energy relative to the spherical field. In an octahedral field, the dz squared and dx squared minus y squared are degenerate with respect to one another, while the xz, yz, and xy are degenerate with respect to each other. So we have a 2-fold degenerate pair and a 3-fold degenerate grouping of orbitals in OH symmetry. Originally, this was derived by considering the underlying physics presented by the field, but we could get to this in a very back-of-the-envelope sort of manner by employing just some symmetry principles. We're working in an OH field, so let's look at the OH character table, and here's an abbreviated OH character table. And what you notice is that the z squared and x squared minus y squared functions form a degenerate set, and the xz, yz, and xy functions form a degenerate set. They're the EG and T2G orbital or sets. What this means is that the 3d z squared and 3d x squared minus y squared must transform as a degenerate set, so they're going to be the same in energy. And the dxz, the dyz, and the dxy also have to be the same in energy. Because of this, we can label those two highest energy sets of orbitals the EG set, and the lower energy set, the T2G set. So we have the EG orbitals that go up in energy by 6dq, and the T2G that go down in energy by 4dq. We're now going to employ the same analysis to a molecule contained in TD symmetry. So instead of titanium hexachloride, we're going to talk about titanium 3 tetrachloride, which is still a 3D1 ion. Employing the assumptions made in crystal field theory, we change those chlorides into negative point charges. And now what we have to do is try to understand how the d orbitals are going to interact with those negative point charges. It's a little bit difficult for me to work with d orbitals when I have a tetrahedral molecule in this orientation, so I'm going to rotate it and think about it as being inscribed on a cube, with the z-axis coming through the top face, the x-axis coming through the right face, and the y-axis going through the back face. We can then place d orbitals within that cube and try to understand how they're oriented towards those negative point charges that we've substituted in for the ligands. When we do this for all 5 of the d orbitals, what we find is that none of those orbitals are directly oriented along the ligand metal axes. They're all off axes. Looking at the character table, we find that the 3D XZ, YZ, and XY have to transform as one set, the T2 set, while the 3D Z squared and 3D X squared Y squared form as another set, the E set. Notice that the G subscript has been dropped because the TD point group does not contain an inversion center. Now if we look at this, we notice that although all of those orbitals are off axes, some are oriented more towards those point charges than others. In this case, we find that the e orbitals are more off axis than the T2 orbitals. Therefore, the T2 orbitals will become more destabilized, while the e orbitals will become more stabilized. This is the opposite of what we saw under OH symmetry. Furthermore, we would expect that the extent of stabilization and destabilization experienced under T2 or TD symmetry will be far less than experienced under OH symmetry because everything is off axis and therefore less strongly interacting with those point charges. So going through and looking at this, in the OH field, as we said, we have the EG set destabilized by 6 dq and the T2G set stabilized by 4 dq. Looking at the TD field, we see the opposite. The T2 set is destabilized while the E set is stabilized. The amount of energy that it's split by in a tetrahedral field is termed delta T, the T for tetrahedral. Delta T is approximately 5/9 delta O if you have the same ligand set, so chloride for chloride in this case. Energy is conserved about that barycenter, so the T2 orbitals go up 2/5 delta T in energy, while the E orbitals go down 3/5 delta T in energy. So now to go through and summarize, crystal field theory is the first quantum mechanical theory that was successfully employed towards the bonding and transition metal complexes, and it considers bonding purely in electrostatic terms. Ligand d orbitals interact with these negative point charges, and that interaction is repulsive in nature. The directionality of the d orbitals relative to those point charges is going to dictate which orbitals become destabilized and which orbitals become stabilized relative to a spherical field. The symmetry of the molecule is going to determine the degeneracy of those orbitals. So we have an EG set in OH symmetry and a T2G set in OH symmetry. For OH, the EG and T2G are split by 10 dq or delta O. In TD symmetry, we have an E set and a T2 set, which is split by delta T, which equals approximately 5/9 delta O. In all cases, within a crystal field model, the energy at which these orbitals are split is going to be strictly conserved relative to the barycenter of the energy of the spherically destabilized orbitals. In the next video, what we're going to discuss are molecules that are in lower symmetry than OH and TD symmetries.